Thank you very much for coming here today. It's the day after Halloween, a Saturday. We're all here and we're happy and excited and awake to learn about some big data. This is a conference all about AI, so you might be asking, why am I talking about big data at all? But the answer is that everything we do, all the fun stuff we want to learn about in AI, machine learning, analytics, all of it is built on data. You build an AI app, that model is trained on data. You bring data, that's your RAG data, your retrieval augmented generation, and you use it and you fine tune it and you capture more data and you see all the things you do rely on data. And so ultimately, we play a lot in environments where the data is shared or already there, and that's fun. But in reality, when you're working for any organization and their data, you're going to have to manage and work with it. And maybe you'll not work very closely with data during your career, but I highly suspect we all will at many times. It may even be our focus. It's certainly my focus. So who am I? I'm Ed Pollack. I'm a data platform MVP in the Microsoft data platform. But as we'll get to in this presentation, the data platform isn't as important as how you use it and why it does what it does. I speak at a lot of events. I love writing about data, talking about data, messing and breaking data a lot. I organize events as well. If you're interested in other professional opportunities, look me up. I post and talk and share information on all different events. And I'll start sharing about Google developer groups as well because they want me to share about their events, and I'm happy to. So thanks for being here today, and I'm happy to be here and talk about data. If you have questions, feel free to raise your hand. If I start ignoring you, it means we're running out of time. Nothing personal, but we're not running out of time yet. I put the TransFinder slide here. You may have saw them out there earlier. They're hiring, they're growing. It's where I work currently. They're always hiring in software development, QA, or non-technical areas. So if you're interested in applying for a job or a paid internship, look them up. But they were already out there talking earlier. I don't have to advertise anymore for them. They did a good job. That's HR. They're better at that stuff than I am. And we already did all this already. You scanned stuff already for them, so that was cool. So what are we going to talk about? Why are we here? I want to talk briefly about analytic data, what it is and where we can store it, an intro to BigQuery. We will get into some of the architecture. I'm not going to go too deep into it because we only have an hour, and in 1 hour you can only do so much, and that's fine. I'm going to talk about some best practices and guidelines, and then come to the fun part where we talk about how analytic data is stored in very similar fashions everywhere, a little bit about maintenance and just how do you maintain big data over time and in the future. And the relevance to all of us is that we have to deal with data no matter what. This is a part of our life, and if you try to read a terabyte of data really fast and you don't think about how you're going to do it, it's not going to be fast. It's going to take forever and it's going to get expensive. So there is a lot of value here in what we talk about when we get past just the agenda into why are we here. The first thing I do want to point out, though, in case you're not fully familiar, is that data can be pretty easily classified into transactional data and analytic data, like apples and oranges. Transactional data is application data. If you go to the bank and do some bank transaction, if you go online and order something, anything like that, that's transactional in nature, where you're operating on very little data, but that data changes a lot. Like I place an order on Amazon, what happens? Some rows go into tables off in Amazon's world, and then that order gets processed. And so every time something changes, we found your item, we're packing your item, we're shipping your item, it's going through the mail, we're tracking your item. All of those are like little changes to a little bit of data, and then it gets to its destination. That's transactional data. So anything transactional in nature, you buy something, you sell something, you go to the bank, you use a lot of your applications and games and things. That's all transactional data. We'll call that the apple, I guess. And then analytic data is data you report on, that you do analytics, machine learning, AI, whatever with. That's big data, and that's the complete opposite. How it works, what is it, completely different. And it's worth mentioning that. So transactional data tends to be, I operate on very, very little data, but I return all the metrics and details and dimensions about it, and I update it a lot, right? Like my order changed, it may have changed in its status 10 times in a row in the course of an hour because it was packaged, it was shipped, it got a tracking number, whatever. I called in because something went wrong. Those are all transactional things. Analytic data is like, I want to know what the sales numbers were for the last year for my organization. And there could be like a terabyte of data there. It's going to scan all of that and figure out really fast. That's analytics. So analytics is less metrics, but mountains of data like this. And transactional is lots of metrics, but far fewer rows. So how do we store this data? So at a very high level, transactional data is stored kind of like this. If you're storing rows or files or however you're storing your data somewhere, transactional data is I want all of the dimensions, all of those columns, all those metrics stored together, because typically someone's going to say, I want my order and everything about it, all 50 things about it. I want the product, the color, the size, the shape, everything. And that would be a transactional read, basically, is give me all the information about like one thing or 5 things. So when that data is stored in any transactional platform, Postgres, MySQL, whatever, SQL Server, a relational transactional database, it's your first row, your second row, your third row. If it's stored in files, the files are also contiguous. My first record, my second record, my third record, and so on, with all that information. That's transactional data, and this is really efficient because if I want to get data on one order, I just grab that little rectangle and I'm done. I got all the information on my order. Maybe it isn't 5 columns, maybe it's 100. But whatever, it's all right there. I read that little chunk and I got everything I need and I'm happy. That's transactional data. Reading 1 row, reading 5 rows, reading 10 rows, super easy. But when I run an analytic query and I say, hey, I want to know the average sale price for this scarf for the past year. Show me the trend over time so I can decide when I want to buy it. You see things online all the time like that. Like, when should I buy the airfare for my flight? Or when should I buy a new laptop? And there's like trackers online and stuff. And that's big data. And big data will generally not scan as much in terms of metrics, but it's going to scan a lot of rows to get information. So let's say I wanted to get whatever column 2 was for like every single row. This storage format kind of stinks, because I've got to read all this stuff and pull out these little red boxes out of all this data. And that's hard, and that's expensive. I've got to basically pull everything back and then rip out those individual red boxes to get what I want. So that's very painful if I have data stored in a transactional world. So analytic data storage, no matter where it is stored by column. And so instead, what you do is every column gets stored separately. And so instead, that top row is the first column, the first metric, and I just have it for every single row, all the way through. So if that first column is an ID, that ID goes all the way through. I have all of them in one place stored together. The second one is the date my order was made. Well, now I have them all grouped together. And if anyone here know how compression works or has a general idea of how compression works or has dug into it before? A few nodding heads. You don't have to know it very well, but in general, the rule about all compression is the more similar things are, the better they compress, right? If I have apples and oranges and try to compress them together, they don't compress so well. If I have a million integers, those compress better. If the integers are similar in value, they compress even better. That's how compression works. The more similar things are, the better they compress. The more different they are, the cruddier they compress. And so the beautiful thing about storing data by column is that the data type is the same, right? One column, one data element, all the same type. And typically the values will be similar, right? If like the transaction order date for my order I placed is a column, well, that order date's going to probably be in the past, however, since I had an account on whatever, Amazon, Target, Walmart, whoever, it doesn't matter. I haven't been alive for the entire history of humanity, so the year is going to be somewhere between like 10 years ago and now. And so now I have a table with millions and millions of dates that are all in the past few years. That compresses great. There's not going to be any dates in there from the 1700s, right? Because there weren't even computers back then. There won't be dates from 8900, because we haven't time traveled to the future. And so they're all very similar. So every column is stored separately, and that makes it really efficient because they're all similar data types, similar values, which is great. And so then when I want to run a query and I say, hey, I want to sum up all of the sales for all the orders for the past 5 years, now I just grab that one row, and I just keep going. All the values for that money amount, and I can just keep going. I show 9 of them here, but in real life it could be millions or billions, but it's really fast because I don't have to get anything else. I just get that one line there of exactly what I want and nothing else. And that's great. This is how analytic data is stored pretty much everywhere by column, and it's very efficient for that purpose. And metadata is stored with it. Compressing data is expensive, and then any analytic data you store is going to be heavily compressed, so it always is going to store metadata with it that tells you a little bit about it. And so along with that row there will be a little bit of data stored alongside of it that tells us the minimum value, the maximum value, the count, the size in bytes, that kind of stuff. It may seem esoteric to you, but any engine processing queries against that data can use that information to make really great decisions automatically. Computers can do that. We're bad at it. Computers are great at it. That's what computers are good for. So that's analytic data storage in a nutshell. But we have lots of choices where we can put it. It can go in many, many places. And we want to make the right choice. And you may have this decision in your career many times. Where do I put data? If you make the right choice, you'll be very happy. If you make the wrong choice, you're going to have a rough time running an app in there. And there's lots of places you can put it. Unstructured data is like just throwing data into JSONs or XMLs or data lakes or a place where you just pour data in, and it sits there, and you pull it out whenever you need it. And it's usually not heavily compressed. It could be. And it generally doesn't have any very rigid structure or relational nature to it. That's great when you have data and you have no idea what you're going to be doing with it yet, or you're not sure what you're going to do with it yet, or you're going to figure it out later. You can put data in a very structured organization, like a data warehouse. Data warehouses are really meant for metrics where you know how things are structured, and you're going to have very well-defined facts and dimensions and things. If you know those things, it's a great place to put data. You know, Big Lake, BigQuery, there's lots of other examples out there of data warehouses, Redshift, and so on. You can put data in files. Files are very often used because they're portable. They can be open source. Avro, Parquet, you can put data in CSVs, I suppose, if you're masochistic. But it's simple, though. You just store data in a text file or anywhere. But there's many, many choices out there, and files are popular because they're portable. I can pick them up, send them over there, drop them, and they're pretty universal, right? You can also use third-party software. If you're in an organization, they may not even do their own data storage. They may simply say, you know what? We use some software hosted over there. We throw our data into it, and they manage it for us. And especially in a small organization, that might be easier than doing it yourself. Or maybe not. And many organizations can make a mistake, too. You can put analytic data into a transactional relational database. That's generally a bad idea. You probably don't want to do that. SQL is not a great place for analytic data. It's just not. You don't want to have a rigid, ACID, atomic, consistent, isolated, durable, transactional database for analytic data, because analytic data is not transactional in nature. It's, I want large quantities of stuff crunched, not give me my order and send it back to me in 5 milliseconds. That's not what it is. Are there any questions, by the way, so far? I tend to go fast. I love going fast. I hope you do too. Any questions? So we're either happy or bored. OK, cool. I'm good with that. So what's BigQuery? BigQuery is a storage engine. It is a lot of things. It uses a data warehouse. It's meant for analytic queries primarily. It's not meant for transactional data. It's meant for big data. And you can put on top of it machine learning, AI, analytics. The key, though, is that it's big. You don't put 1,000 rows Hable into BigQuery. You can, if it's going to be used, the bigger stuff. You put big things in here. You put, gigabytes of files. You put millions or billions of rows. You put big stuff in here. That's what it's for. It's meant for that. It's going to heavily compress it and make it perfect for whatever machine learning AI applications you want to throw on top of it. That's what it's meant for. BigQuery specifically is managed in Google's cloud. It's one of those things that's fully managed. They give you lots of numbers. That literally is the uptime they promised. I had to check my numbers. But that's how the cloud is, right? It's up almost all the time until it isn't. And then, I think was it last week? AWS had a giant outage last week. And everybody was freaking out because their Minecraft wasn't loading or whatever. There were more important things that didn't load too. But that was one of them. But Google, Google Cloud, because it's Google Cloud, they fully manage it. So security, encryption, uptime, you don't worry about that. It's just stored in the cloud, which is nice. That is nice. So like everything I mentioned so far, analytic data is stored by columns, so is BigQuery. So every column gets stored separately. You can access it with SQL queries. It isn't a SQL database, but like a lot of things out there, everyone thinks SQL is going to die. SQL never dies. We all query everything in SQL anyway, or through some other method that actually uses SQL. It just never goes away, and that's fine. The metadata is free, so whatever data you store on BigQuery, it's going to automatically store metadata about your data. Metadata is just descriptive data. It describes something else, which tells you all about it. You can investigate the metadata if you're curious. You don't have to. It'll automatically use it to make smart decisions. So those metrics here aren't just academic. They allow it to optimize the queries. So if you have 100 billion rows of data and it's all organized, it can automatically skip whatever isn't needed based on that metadata, which is really nice. Because reading 100 billion rows of data would take a while. Reading a teeny fraction of it can be kind of fast. Compression is really, really important to all analytic data storage. If you're storing data for any real AI or machine learning applications and it's not compressed, you're making a mistake. It probably is, though. Any application you store the data is going to be heavily compressed, and it has to be. Data compressed by column automatically compresses very, very well. There are many algorithms used if you care about them. There are things like bit packing, dictionary compression, run-length encoding. If you don't care about them, no big deal. But the key is that repetitive data compresses really well, especially analytic data. So you can see a gigabyte of data become 20, 50 megs, 100 megs. It can shrink a lot. Of course, means that terabytes become tinier, petabytes become even tinier, and that's good. Their storage format is proprietary. They call it capacitor. That's what Google calls their storage format. Sounds fancy. They own the format. They don't give out all the details, but I'm going to tell you a secret. We can know most of the details, even if they don't give them to us, and that's fine. They tell you just enough that you can sort of figure it out, and it's based on a lot of open source formats. So like everyone else, they had an open source format. It was beautiful, and they turned to a closed source format. Now you don't know it all, but that's fine, because we know how it works, and we can figure it out. Here's some very quick compression demos. The secret here is that every analytic platform uses these, I promise. What I'm showing you right now are examples of compression. You don't have to know how it works exactly. I'm using desserts, by the way. Desserts are fun. I like baking, so I like sweets. I had carrot cake right before I came here today. It was delicious. Anyway, I'm going to talk about a few encoding methods just really quickly to try to show how compression works. So imagine I had a very long list of desserts. Those over there are the size in bytes. These are just not Unicode. They're single bytes, so every character is 1 byte of storage. I'm going with a very simple assumption here. So my total data size, imagine I'm a bakery selling stuff, is 203 bytes. That's it. So 203 bytes for that. Now imagine it's like a hash table, just like you're working on a program, it's a hash. And so I create a dictionary. Every distinct value from over here gets a value over here. So now I took the size of my dictionary, just 1 time for each value is 82 bytes. So now I've gone to this trouble. I've made a hash table of all the distinct values in my data set. And now I just say, hey, I have my dictionary. Now I can just have that little itty-bitty index ID be my link back to the data. So instead of storing all those text strings over and over that could be long and verbose, I'm storing a 3-bit numeric, 0, 1, 2, 3, or 4. That's just 3 bits. So that's now 33 bits, about what, a byte, like whatever. 8 bytes, 4, whatever. I'm trying to do math on the fly. I shouldn't do that. It's a very bad idea. But I've shrunk from 203 bytes down to like a little over 82, all by just making a hash table of values and using it. That's dictionary compression. It's used in every analytic storage format in the world. If it's not used, they probably don't have a very good storage format. Because it's necessary. All strings and big, clunky data, this is the best way to compress it. Bit packing is really easy. All bit packing is it takes all the excess zeros off. Because it turns out that most data types, and you may have encountered this in programming, have fixed width. They're assigned up front. Like an integer is 4 bytes, done. 32 bits. Doesn't matter how you store it or what you do with it, it's 32 bits. Many storage platforms put it that way, but in the real world, not all the values are going to be 32 bits long, right? I'm not going to have 2 billion as my value. In fact, most times you work with numbers, they're a lot smaller. They could be status IDs or data identifiers or things like that that are much, much smaller. Or how many days have I been alive is smaller than 2 billion. It is. So you can take the 32 bits for an integer and say, you know what, my number has a whole bunch of leading zeros in front. I'm just going to ignore them. All I really need is a signifier for where my number begins, and I'm good. And so now instead of storing 288 bits, I store 108 bits. Again, great for numbers. Decimals, integers, any kind of numerics. Shrinks it down to nothing. You can do it on dates, too. Dates are really just numbers. Times are really just numbers. They're all just numbers. And so they can all be shrunk down. This is a really simple algorithm used everywhere. Get rid of all the extra zeros. Many data types are fixed width. That fixes that. Because for analytics, you don't need all the extra zeros. It's not going to change much. So the beauty of the analytic data is it doesn't change as much as transactional data. So you can compress it more heavily because it won't change as much. So just 2 examples of compression and how it works. Another fun thing about analytic data is that data order actually matters. When your data is ordered by something, anything meaningful, it compresses better. Even if you don't believe me, it's true. The most common thing that data will be ordered by in any platform is date, because data from today is more similar to data from yesterday than data from today compared to like 10 years ago or 15 years ago, or even 5 years ago or 1 year ago, because things change. All the details change of who's storing it, what's being stored, the details about it. I used to buy this pair of jeans. They stopped making them now. I buy this pair of jeans. Well, in whatever place I ordered it from, the numbers changed a little because they don't sell the old one anymore. So things change. And so the cool thing, though, is that when analytic data is stored, it's not like a transactional database with primary keys and stuff and clustered indexes. The order can be adjusted by the engine automatically. So you store the data, and it can automatically order chunks of it for you, just in the background. You do nothing. It won't affect your queries, it won't affect your results, but it's going to order it for you. And so Capacitor, just like a lot of other platforms, will automatically sort data for you in chunks in the background. And it's a really complicated problem to solve. It does it in the background, but it can do it with enough success that it makes a big difference. So by sorting your data, it actually will compress way better. And by way better, I mean 2 to 3 times better. It's not even sarcasm. When data is sorted automatically or ordered, it stores better, which is very, very useful. In BigQuery, they break all your rows down to chunks of rows and call them shards. So if you had 1 billion rows, it would take it and chunk it down to like maybe 1 million or 2 million at a time. It's automatic. And then each of those will have each column compressed separately. So it's taking your data and automatically breaking it into small, bite-sized chunks, compressing the snot out of it after ordering it, and then it stores them all separately. And so your data, ultimately, isn't just a pile of data. It's lots and lots and lots and lots of little pieces of data, all stored separately alongside each other, with just enough information to find them. Yes?
So if I run the machine learning analytics on transactional,
I can't hear you. Sorry, what?
if I run machine learning analytics on transactional data, let's say it's taking about an hour. If I use the BigQuery, it automatically does the transformation, and then it will speed up that algorithm as well.
If you're doing analytics on transactional data, you're suffering because it's going to try to read data with all the columns intact, but your analytics usually don't want to do that. And so you really want your data stored in the analytic form. It can be any analytic format. BigQuery is one if you're in the Google platform. But you want your data in analytic. You're going to have a very, very hard time doing big data analytics off of transactional data because it's not built for that. Transactional data is built for, I want lots of columns, but less data. Analytics is, I want less columns, but sum them all up. Give me a sum over a lot of them.
My question is, does it do automatically? If I pump in transactional data, does it converge into analytics?
No. If you perform analytic queries against transactional data, it'll do the best as your data architecture is built for. It's going to probably be slow and expensive. It can't automatically translate. You can't translate. It's the apple and orange slide from earlier. You can't translate analytics to transactional and back and forth. Like in your mind you can, but the computers aren't good at doing that. So you've got to basically have analytic data stored for analytics, transactional for transaction. And what often happens in the real world is that people build a small database somewhere, for transactional stuff. They begin running reports against it and dashboards, and then it gets bigger. And then one day it just gets a little too big. And you try to run analytics, and it's too slow because the transactional data got giant. You now have 1 billion orders instead of like 1,000, and now it's slow. At which point you've got to say, all right, where am I going to put my analytics stuff so I can run that fast? I want to run machine learning, and I want it to run fast. I don't want to wait an hour. And that's the challenge you hit, is you can't use apples for oranges and vice versa. So here's kind of a graphical representation of what I talked about. Yes, they call them shards. You can laugh if you say it fast. It's funny. But basically, the way they do it is they take, let's say you have a giant mountain of data. You put it in BigQuery. It's going to break your data up automatically into chunks of rows. The amount varies, but it's around 1 million to 2 million on average rows of data. And then within each of those shards, each column is stored separately and compressed. So really, the number of each of those little boxes is a separately compressed chunk of data. The number of those that you have is going to be equal to the number of columns times the number of shards. That's it. If you have 100 million rows stored in 50 shards, and you have 6 columns, 50 times 6 is 300, done. That's how many chunks of individually compressed data there is. What's cool is that metadata describes each shard. So each shard will have data that says, all right, for every column, here's your min and max value, the count, are there nulls, how big is it? And for you as a human, that data is trivia pretty much. It's interesting, it's academic. But for the engine, for that capacitor engine, it can check that metadata in microseconds and decide, hey, shard number 2 only has dates between January and February of 2025, but you're asking for dates from March. I can just skip that one. I know it's not in there. My metadata tells me, and I can skip it. In the real world, you could have thousands or hundreds of thousands of shards. It could be huge. And it'll all be ordered kind of by date, probably, because data is created in order of date, right? Like time goes forward, correct? Generally speaking, goes forward. Unless you're watching like Doctor Who, it goes forward. And so at any point, somebody may say, hey, I just want to get data from January 1st through 7th, 1 week. And the engine knows all of that ends up in one of those. It can skip all the rest automatically. So instead of reading terabytes of data, it reads a teeny little sliver and is done, which is really cool. On the flip side, this is again where transactional databases suffer, is analytic data. Again, each of those columns is stored in separate chunks. So column A is not stored in the same piece of storage as column F. And what that means is that if I run a query saying, sum this column for this date range, all I need is the column and the date range, those 2 things. I can just automatically do that and skip the rest. So for this example, if I just needed 2 columns, I can skip the rest automatically. No effort needed, just skips them because it knows. I'm not asking for the color or the shape. I'm asking for the date, and I'm asking for the price and nothing else. So there could be 100 columns there, 1,000. It doesn't matter. It'll skip all the ones it doesn't need done. And that's one of the biggest pieces of value over transactional data is it can't do that because it stores all the columns together.
Control for charts, like partition.
The control is the order that you put the data in is going to be the order that it creates that in. So it's going to create it in the order that you store your data. So if I begin inserting data, it's going to create those shards in the order I inserted it, pretty much. If for some reason your order stinks and you're getting very inefficient queries, you can go and do it again. You can take it all and create a new one and put it in a different order. You may never need to do that, but it's a useful tactic if you ever have to do it. It's a good question, though. You don't really control it except through the order you put the data in. It will do all the creation of these things on its own. You really don't want to control it. That's too technical, too detailed, and nobody wants that kind of nitty-gritty control, even me. And I love nitty-gritty control. So.
My thought was like usually per K.
Yep.
Where you usually per K, you got the ability to partition based on your specific data fields.
Yep, and that's coming later. So partitioning and V-order and Z-order and all that cool stuff you can do in Delta Lake and like Parquet, all that kind of functionality is here too. In fact, the Parquet storage format is disturbingly similar to BigQuery. I'm going to mention it later on too, because there's such similarities there. So here's a really quick example, by the way. I gave the example earlier of desserts, and that was how we stored it in the left, right? This is exactly what I had in my earlier slide of the storage, and notice that the index IDs there are kind of scattered and out of order. And so if those are my dictionary encoded data, if I reorder it, it compresses nicely now because anybody know what run length encoding is? Run length encoding is one of the more commonly long-used compression algorithms that says that if things are like consecutive, they're the same, I can just group them together and describe them as a value n times. So if within a data set, a value of 50,000 occurs 10 times in a row, the engine will automatically store that data as 50,000 10 times instead of 50,000, 50,000, so on and so forth. And so this is just kind of how ordered data can now be chunked together, and you can do this. And I can say, you know what, instead of me storing 0, 0, 0, 1, 2, 2, 2, 2, whatever, I can just say 0 3 times, 1 1 time, 2 4 times, so on and so forth. So this is like the value of ordered data. But you don't have to really worry about this because the engine does this for you. They'll all do it for you. Now, the big key to all compressed data, all analytic data is heavily compressed. And what that means is that decompressing it is a little expensive to read it, but not too expensive. But writing the data is expensive. And so unraveling it, decompressing it, and then storing it back again is expensive. So whenever you write data, the engine is automatically built to not immediately go in and rewrite what's already there. So what really happens in BigQuery and everywhere is when you delete analytic data from a big data solution, what it will do is soft delete the rows. So if I have a billion rows of data and I go in and delete one, it's not going to say, OK, I'm going to take the shard, I'm going to decompress it, remove that one row, and then recompress the whole thing. For one row, that doesn't sound too bad. But if you went and said, I want to delete 1 million of them, and they're all over the place, well, and I have to take 1 million shards, and I have to decompress all 1 million shards, and then I have to, no. That's going to take forever. You will wait for hours. And so what it does instead is it soft deletes. And so it's going to basically just take and put a little flag next to any rows that are deleted, done. And when you read the data, if it sees that flag, it just skips the rows that aren't needed, done. It sounds complicated, but it's much, much faster and more efficient for a computer to do that than to say, I want to decompress everything, change it, and recompress it. Because we want analytics quickly. We want to write our data and read it really fast. We don't want to wait forever. And then in the background, it'll asynchronously clean it up later at its own time frame when there's resources available. That's proprietary, but it doesn't really matter. You don't really care about that. The soft deletes eventually go away, and life is good, because the process of decompression is very expensive, and we don't want to be constantly rewriting our data. Here's most of the data stored in metadata. I mentioned this earlier because it's important, but now that I've described a lot of how BigQuery works, it may make a little more sense on how valuable this is. And so metadata gives the engine information. Has anybody here ever written queries before for any database structure, any language, any database? Some hands. When you write a query, you typically are going to have a select and some columns and a from and some filters like a where or a group by or whatever. And those filters are key. And so the filters tell the engine, BigQuery, hey, if I have metadata about mins and maxes and row counts and can there be nulls and things like that, it can go faster. For example, if I say, give me all of the rows from this data that have null, if null isn't allowed or null isn't present for some of the data, you can just skip them automatically and go really fast. These conventions make it so you can read billions of rows in seconds, which sounds ridiculous, but it can do it because that teeny bit of metadata that's there can short-circuit the whole thing. It's like if I went up to you and I asked you a question, hey, is your birthday on October 32nd? You wouldn't have to actually think about it. There's no 32nd in October, you're done. Like, the question's already answered. And so the metadata essentially lets us just QED the whole thing, go right to the finish line, and decide what it needs without having to actually read the real data. Because reading data takes time, but reading little 8 bits of metadata is very fast. Here's again to what you were talking about before, partitioning and clustering. Even with all these conventions I talked about, the compression and the metadata and only reading certain columns or rows, when you have enough of it, it still gets slow. And these are newer conventions in the analytic world that didn't exist 20 years ago or 10 years ago, but exist now. And that is, oh, you have like 1 trillion rows, or you have petabytes or exabytes of data. When you're at that point, you've got to do more. And so what you then say is, OK, I want to partition data. Partitioning says, I'm going to choose a key column or set of columns. Usually time is what you want, but not always. And I'm going to then take the data and subgroup it further based on month, year, quarter, whatever. And then that subgrouping allows for even faster querying, because now if I have all my data for 2025 here, and all the rest is over there, and you come along and ask for data from 2025, I can automatically ignore all of that. You know, if you have data going back to like 2000, I can ignore 98% of the data and go right to here. And realistically, when we talk about data in applications, most of the time, what are we talking about? Current data, recent data, right? How often do you go onto like any ordering platform and say, give me an order from last week? That's pretty common, right? I want to know what happened to my order. It's not arrived yet. I'm mad. I want my shirt. I'm actually waiting for an order right now today for a new pair of gloves. But how often do you go online and say, I want to see my order history from 20 years ago? Like, how old were you 20 years ago? Is it even relevant? Like, does it even matter? Do I check that? I don't care what happened 20 years ago. My order could be deleted from Amazon. I don't even care. I don't know. Like, it doesn't matter. And so partitioning lets you take data and group it into new data and oldest data. Because we know that the newest data is queried more often, and older data is touched less. If you use social media, you know, Instagram or Twitter or anything else, they very often show memories to you. Like, here's your memories from October 31st, the past 10 years, and that's intentional. They intentionally serve that up to you so that it's already cached and ready to go, because there are very few other reasons you'd ever go back in time for anything, aside from what did I do 10 years ago on this date. And so instead of making it inefficient, they automatically give you that data cleanly. But more often than not, people don't go after data that isn't new or newish. And then there's clustering. Clustering in BigQuery is basically your way to say, you know what? Data's great, but I also search for data very often by other metrics, like maybe an account ID or a person ID or something else. You might do that in your ordering system, right? Like, give me all the orders ever throughout history for one person, one customer, and that's cool. So clustering is your way of saying, you know what? I want to index by a different column that may not be date or time. That lets you do it. So if I have an oddball scenario or a different scenario to query by, I don't have to read everything. And you'll know, when you read everything for any reason, you'll know. It'll be very, very slow. That's when you wait an hour for something and you're sad. Like, all right, run my cool machine learning algorithm. I finished it. I trained. The model's working. Go. And then it doesn't finish for a day. You might be OK with that for something academic. But in the real world, nobody wants to wait a day or an hour or even seconds. Like, who here, when they load up an app or a web page, will wait more than 5 or 10 seconds before they give up and move on? I'll give up. If I load an app and it's not up in like 10 seconds, I'm on to my day. I'm done with you. I don't have time for that. Nobody does. So there's even kind of a bigger encapsulating thing in the Google world called Big Lake. Big Lake is essentially a kind of a wrapper for even more data types. You can basically throw into there data of many, many, many types. So if you have analytic data that isn't just in BigQuery, you may have Parquet files, CSV, Delta Lake, Iceberg, Avro, you name it. These are all stored. If you're not familiar with them, that's OK. Basically, all of these are examples, they have many more, of analytic storage formats. And if you work with them, they're stored very similarly to BigQuery. But basically, Big Lake just lets you throw all this stuff into it and use it and query it. And so you can query your BigQuery data and your Parquet data, CSV, text files, whatever. You can throw it all in there and query it, and it will do the work of indexing it for you and making it efficient. Though, to be fair, if you're going to do it for really serious analytics, you should put it into an analytic format. Like a text file or a CSV is not really an analytic data format. That's just a pile of stuff that I threw somewhere. It's a stack of paper. So it's not, if you're doing analytics off CSV files or text files or uncompressed stuff, it's going to be rough. You don't want to do that. But basically, the ultimate goal here is you want to integrate with lots of formats. It works. And many of these are open formats. So you can just take them and plop them in and use them and take them out, import, export, no problem. Now, the fun here, it's worth the good mention, kind of the punchline of this whole presentation is they're all the same. And if I had like 6 hours, I would go into detail as to how they're all the same. But this is the key. Every analytic storage format in the world right now is stored very, very similarly. There are differences, like some may have different engines, they may have slightly different compression algorithms. We have our proprietary thing, they have theirs, but it's all stored by column. It's all stored using a whole variety of compression where I'm pretty sure they all have bit packing, dictionary encoding, value encoding, run length encoding, et cetera. There's lots of, they all have ways to reorder the rows and do all the things I mentioned. They all do soft deletes. They all stream their writes in. That means if I write a row of data, it doesn't stop the presses, decompress a shard, put the one row, and it recompress the whole thing. Because then what happens when I insert like 100 rows or 1,000,000 rows? They all have ways to streamline the writes and make them really, really fast. They have to. If I want to, because big data is different than small data. You know, if I'm placing orders online, how many orders can Ed place at one time? Like 1, 5, 10? I've never placed 1 billion orders at one time in my life for anything. Is anybody here? 1 million? Even 10? Has anybody ever placed 10 online orders at one time in one transaction? No, not really. You may order 10 things. You're not going to place 10 orders. And so as a result, when you write data, you're writing a lot of data at once for analytics. Transactional is not like that. So when you're writing analytics, they have all kinds of shortcuts to make it so you don't have to actually write the data for real. You stream the writes in, you stage it automatically does everything for you, and this is all invisible to you. But they're all very, very similar, and if any of them use SQL or a very familiar language, you can use Python a lot too. The number of languages to hit your data there's a multitude of them, but many have similar backends. So here's an example of some stuff I lifted off the internet. Snowflake is a pretty popular data platform out there. A lot of companies use it. It's expensive. So if you haven't used it, you're not missing much. But I just went to their webpage, and I just screen grabbed stuff that describes their platform. Now, Snowflake's proprietary. That means they don't tell you how it works. They charge you a lot of money for it. Trust me, they charge a lot of money for it to use it. It's fully managed. But if you look around, if you've been looking through here, you'll notice stuff that is similar to what I said before, like the query processing, column, internal optimize, compress, columnar format, metadata management, query parsing and optimization. What they're basically saying is we do exactly what I just said you do, but they just charge you a bunch of money for doing the same thing. They don't tell you how to do it. And this is valuable. Time travel is something else that we could talk about if we had more time. Almost every service, BigQuery, all of them offer time travel, which basically is they'll keep history of your changes so you can go back in time and say, I want my data from a week ago. I want this value from a month ago. That's all time travel. Isn't fancy? They're just copying data. That's all it is. It sounds fancy. Time travel. Wow, you're like the doctor. Awesome. But it's not. It's just they're copying your data. Yes?
What would be considered a more cost-effective alternative to something like Snowflake?
There is lots out there, and honestly, the most cost-effective choice will be one of two things, because you're not going to get a choice most of the time. One, if you're doing a project on your own, will be something open source where you don't pay for it. If you're working for a company or organization, though, odds are the most cost-effective thing is whatever they already use. And this is the reality of data platforms and really any platform, is that we're all going to learn one and go out there into the real world and eventually use a different one. Because you'll discover, here's a company, and they all use Google Everything. Cool. I use Google Everything. And for them, the most cost-effective thing is something on the Google platform because they already pay for it, they already use it, they're invested in it. And then you go somewhere else in your career, and they use Microsoft Everything. And they're heavily invested in Microsoft. If you tell them to change, they'll laugh at you because they've already spent a bajillion developer hours on Microsoft. And you go over here, and they're using Amazon, and it's the same thing. And so the most cost-effective approach is going to be either open source or the same data platform you're already using for everything else, which sounds like a cop-out, but it's true.
Do you have like a product in mind?
For storing analytic data, I had kind of a short list back here. Delta Lake is an open source format. Parquet is an open source format. You can always store data as flat files if you're adventurous. Those are all choices. But those are the easiest things that are going on. There are lots of other platforms that provide free storage. All of them do store, all of them allow you a free storage. So if you want, as a person, an individual, you can go out to any of these data platforms, Google, Microsoft, whoever, and they have platforms that let you store data for free for a while. So if you do want to learn a platform, a bigger platform, you can do that, and it will be free or cheap.
Yeah, I was referring more to, like people who can't afford like an Office 365 license.
Oh yeah, and even if you can't afford the licenses, like there's still free stuff out there you can use. You can, Azure has free credits. SQL has Express and so on, developer editions. Like you want to do SQL Server, developer edition is fully featured, it's free. You want to do, so there's, Google's the same way, Amazon as well. They all have free tiers where you can store enough stuff to be useful and do things, but eventually you're going to outgrow it. And that's going to usually be when you have a product and it's making money and you're selling a lot of it. But at that point, you can afford something, right?
Could it be the reason why they're so expensive is because there isn't anybody out there that can do what they did?
They're expensive because they're geared more towards large organizations who have outgrown the do-it-yourself. And large organizations happen to have a lot of money, so they can spend for it, that's all. And so,
Take a look at Apache.
Yep, oh yeah, Apache.
With Apache offers some open source tooling with things like Iceberg and Parquet that are readily available, easily adoptable for people that want to spend on those services.
Yep.
Look at Parquet, look at Iceberg, Delta. That's the stuff that people build with behind the scenes. And most of those projects, you're going to see those tools are the basis that Google built in, or AWS built into their product. So always go to things like Parquet.
Yep, very true, very helpful. And yeah, Apache, Parquet, Iceberg, Delta, they were invented by Apache.
Is that more cloud or on-prem?
It could be either. They're just file formats. They're open source. You can use them anywhere.
Makes Snowflake more attractive as more cloud-driven?
Yep. Everything is cloud-driven, or you can do it yourself. It doesn't really matter, honestly. I will say, though, one nice thing about those file formats is they're open source and portable. So if you outgrow something, you just pick them up and move them somewhere else. So I'm going to keep going here because there's some value to be had at the end here. There are best practices that apply to all analytic data platforms, and I do want to hit those before we run out of time. This is important. If you're managing big data for analytics, for AI, for machine learning, and you have tons of it, there are certain things that are valuable to know. Number one is never update data. Now, I'm not saying you shouldn't write data. We all have to write data. But you want to create data. That is like an insert. You can delete data. That's a delete. But updating is super expensive because most of these engines like BigQuery are still transactional in nature. Like, they still guarantee you that things will be consistent. Not eventually consistent, but now consistent. And that means that if I run an update, it's got to go in there and say, all right, I need to create some new data and delete some old data and do all of that in one shot before I let anybody else touch the data again. Now, if you update a lot of rows, that becomes really expensive because now they have to stop everything. Not just soft delete a few rows, route a little bit of data, but stop everything. And I made this mistake one time in a production environment. I went in and thought it would be cool to update 1 million rows from a giant data warehouse, and the server was brought to us. I had to stop it, turn it off, start over, and it turned out all I had to do was just change it to 1 million inserts and 1 million deletes, and it was fine. Not even joking. So the word update should really never occur much in analytics. It really is. If you structure your world as inserts and deletes, your life will be easier. Just trust me. Second piece of advice is never grab everything. Select star is a no-no in the world of analytics. If you have a table with 100 columns and you try to query all of them, it's going to take forever because now you're reading all the compressed data for 100 columns. But if I say, hey, I just want to run some analytics on these 5 columns, that'll be fast. That'll be 1/20th of the speed. Sorry, 20 times faster. You know what I mean. You know what I mean. Much, much faster. Giant inserts and deletes are fine. They don't care. All these platforms are built for big data. If you insert 10 million rows at once, it's fast. If you delete 10 million at once, it's fast. Don't worry about it. When you're in the transactional world, those things are slow. But in the analytic world, they expect it. It's fine. Don't worry about it. Make sure everything is filtered, though. If you read data and don't filter it, it's got to read everything. That metadata becomes useless. So if you have 1 billion rows and you don't filter it, it may be able to do some trickery to help out a bit, but you're still going to read everything because you're not filtering. Always have filters. Filters are good. filter by a time dimension or something meaningful, and a lot of it goes away. I do mention that nothing is free. That's important because nothing is free. Every tool has limitations, and you can abuse it. It's very easy to use the wrong tool for the wrong job and get in trouble. And so everything I'm talking about here today, I mentioned BigQuery and Parquet and everything else. This is all for analytic data. Big analytic data. Not for small data, not for running a bank. It's for giant analytics. It's for machine learning. It's for AI. It's for I want to crunch a mountain of stuff and get results. So I want to leave time for a few questions at the end before we wrap up. But the big key here is that BigQuery is, if you're on the Google Data Platform, it's a great place to start. They have free tiers. You can use it. But the fun here, we're at a Google Developer Conference. We talk about Google. But it's stored the exact same way as every other analytic data platform in the world. All of them. They're all stored the same way, which means whatever you learn on one will apply to the rest. Your best practices about how to best manage it, best query it, speed, performance, everything, it will be the same in every format. It doesn't matter where you are. It doesn't matter whose cloud you're in. It doesn't matter what kind of file format. If it's made for analytic data, it will be stored very, very similar. The best practices are the same. And they will all, there's your little list in the bottom, all these things I'm listing out here, Hadoop, Synapse, Redshift, Orc, you name it. They're all analytic data platforms. They're all ... stored the same basic way. And that's really, really critical. They will all claim they're special and unique and better than the other. That's fine. We're allowed to do that. We all love our own children better than other people's children, right? I get it. I have 2 boys. I love them a lot. But they're my kids, so I love them more. And that's fine. That's how it is with this too. And so it turns out, I'm not saying all kids are the same, but all analytic data platforms are very, very similar. So as you learn how to better use them and work with them and manage them, if you end up using a different one, don't be afraid of it, because all the best practices still apply. All the ways to get the data faster, all the ways they manage it, compress it, deal with it, it's all basically the same. And knowing that, you'll have an easier time in your career as you jump from one to another, or you want to change for some reason, do something different. And so that is the growth thing you mentioned too. Like, I want to start somewhere free because I don't have any money, but one day you may need something else, and that's okay, because something else is stored the same way. So, are there any last-minute questions here before I hand it off to the next speaker? Yes?
I will give you an example, then you can tell me how can I use the data in the best way for this case. So think about I have a marketing, and then I'm looking at different profiles from different platforms, for example, YouTube and Facebook, and I'm starting their profiles with their comments and the posts and everything else of those things. And I want to know about like average likes that they got on the posts, something like that. So I have a lot of stuff that I need to store at the same time, but I also need to consult them quite often and ask questions that are average and sudden and stuff like that. What's going to be the best solution for a case like that?
So it sounds like you have a scenario you're searching lots and lots of text, right? You have tons of text, and you're trying to search and get insight out of it?
Yeah, it's just text and images.
Yep, text and image. And so BigQuery is not for text and image. It's for data. That's what it's primarily for. If you're using text and image, you want something that has semantic search, that has image analysis. Big Lake is a place to put it, but you really want it in a format, either you've got to be searching all that text constantly, in which case you want it in like Elasticsearch or a text format that's built for that, or you want to index that data in a meaningful way. Many organizations, what they will do is take their mountains of text and vectorize it. They'll throw semantic search at it, vectorize it, and that'll basically turn it into numbers. And then once you have numbers, you can do this with it. And that's what they ultimately do, because you want speed. I don't have time. If I'm searching at runtime, I can't search 1 billion text files all at one time and get results every single time. And so what any real engine will do is index that data in a meaningful way with vectors or metadata, and then query that. And so depending on what your application is, you may do that in many different ways. But if you have like a terabyte of files, you can't read a terabyte every time I want to do anything. Nobody can. It takes too long. So you've got to create insights on that data meaningfully so people can get the insights instead of the data. Any other last-minute questions? There is a session in here at 4. Is there a speaker in here for the next session yet? If not, this is a free-for-all until then. Are you the next speaker? Okay, cool. I don't want to take my time too much. You have 3 minutes. So any other questions you want to throw out here before we transition to the next session? Yes?
So if you're partitioning by date, how do you handle the case where, say, you're partitioning web traffic by date and you have one day, huge spike in traffic that partition?
So what will happen is, if you do nothing special, then your partition that has that one special date will simply be bigger. And that probably doesn't matter. If like a partition is bigger by like 1 million or 10 million, in the grand scheme of things, to a format like this, or an analytic format is nothing. To an analytic storage format, 10 million of something is nothing. Even 100 million isn't that much. Now, if it was big enough, you might want to create a subpartition and say, all right, we're partitioning by year, but for this one special year, there's some noise in it. Or you could go in there and clean up the data, I suppose. It really, this also could be simply an outlier. Like you had one outlier in the history of an organization. How do you handle your outlier? And so you really have two choices. Most organizations would simply tolerate it. You'll have your data, and one chunk of data will just be bigger. But its odds are it's not going to be so big that it's going to break everything. Because again, this is built for analytics. And so if it's a billion instead of 100 million, no one, it's not going to care. You won't notice it. You won't even notice the difference in speed. You won't. If it's 100 billion instead of 5, that's a little weird. I'd probably have questions. But in general, traffic spikes aren't a problem.
If you're trying to do something beyond just counts, it's going to be a lot more difficult. You're not going to have a big problem if you're doing count limits or something like that. You're trying to do massive relational work within that. Structuring the data will be good to make that.
Depends what you're doing, but yeah. 100% true. So I want to turn this over to the next speaker. If anybody wants to chat any further, I'll be around, but I don't want to overstep the next person who's talking, because that's not very nice. So I'm going to pack my stuff up now. But thank you very much for coming and listening to a session all about data. You are very tolerant listening about data, so thank you.